Okay, so this is the W cycle. I won't draw it because it'll take the whole whiteboard. Right. So the first component of multigrid is the smoother. We already talked about it, right? Here we use Gauss-Seidel, and the primary requirement for the smoother is that it should tune down the high frequency component of the error. So, for example, Jacobi, plain Jacobi, non-modified, is actually not a very good smoother. Why? Because if Jacobi is not a good smoother, because Jacobi involves dxk plus 1. Let's just write down the error equation, right? So E of k plus 1 is equal to minus d inverse L plus U times e to the k, right? Right? Okay, so for Laplace equation, for example, and what is a good smoother may depend on the equation. Right? For equations with second order derivatives, Jacobi is not a good smoother because this operator D is just a scaling, right? D just scales each individual grid point. L plus U is it's like a large number. It's like the Laplacian operator plus a large number, let's say plus let's use small a, applied on the ek. And what you have is that so another point of view is if you think of what this matrix is, it's in a 1D it's basically half, right? Half, and all the way to here. And if you think of what does it do, it's basically taking whatever solution you have, whatever solution error you have, and take the average of the two grid points and get to here, right? So for most kind of solutions, it actually smoothes out the solution error because it just takes the average between neighbors. But there is actually a particular kind of solution that the Jacobi iteration is actually horrible at smoothing. That's a grid by grid oscillation. So if you have a solution like that, if you have a solution error, you always have in the beginning you have just an arbitrary initial guess, and the solution error is basically the exact solution minus the initial guess. And that solution error can contain all kinds of components, right? So if you can smooth some component of the solution error but not others, that's not good. You have to be able to smooth all components. And Jacobi iteration cannot smooth this component because every time you take an average, you get to here. You take the average of these two, you get to here. So after one Jacobi iteration, the solution error becomes this. It's just gets flipped over. It's not reduced pretty much at all, right? It's only reduced near the boundaries. So this is why Jacobi iteration actually doesn't by itself serve as a good smoother. What does serve as a good smoother is this called under relaxed Jacobi. So that is, what if I don't make this all the way to half, right? But make it, let's say, a quarter. So what if I can perform an averaging like a quarter, a half, and a quarter, right? I have half on the diagonal, a quarter on the lower and upper diagonal. That will be a very good smoother. If you take this matrix, take this kind of weighted average on this grid by grid oscillation, it's gonna be reduced by a lot, right? So the idea is when I split the matrix, I put more on the implicit term. So instead of decomposing A equal to D plus L plus U, I decompose A as some, let's see, I want to put some L plus U minus a factor, let's say alpha times D. Now here is 1 plus alpha times D, right? So what happens is that I want to have more weight on the implicit component just by scaling the diagonal a little bit, and on the explicit component, I still have so instead of in the Laplace equation, the D is negative, right? After this minus alpha, this diagonal becomes positive and becomes a very good smoothing average. Right, so basically this is the requirements on the smoother is that you have to be able to smooth all components of your solution area. Otherwise, that component is going to give you trouble in multigrid.